Hello, everyone. We have a nice, cozy crowd here. We were fully booked, but we were around 50% full. So. In any case, I'm Jeff Smilow, the Executive Vice President and Director of Building Structures for WSP USA. I'll be beginning the presentation, and then I'll be handing it over to Michael Gustafsson from QNEC, and he'll talk about how the QNEC product can help us with our goals here in delivering projects. And behind me is Joe Fiorello. He's our CAD director of the WSP New York office, CAD and BIM. And we have Sean Sinnett, who's one of the directors for our fabrication modeling office, the Tekla 3D work. So let's begin. What's Constructible BIM? What am I talking about? Constructible BIM early connected models. Simply put, it's how to link your design models, which most people in my industry use Revit, how to link it to the fabrication models, which could be Tekla, it could be a variety of other software packages that fabricators use in preparing steel, mainly steel. That's what this is going to talk about. So that's what we call the connected models, the fabricator's model. We use that term interchangeably, the fabrication model. So how to link the two processes. And this is, by the way, not speculation or theory. This is, I'm gonna walk you through practical implementation that we've used on very significant projects. And we'll talk about how we did it and the benefits, which are significant. And then it's up to you whether you want to do it. Hopefully you will. So here's our table of contents. We're going to talk about general big picture, the benefits of this process. Then we're going to get specific. What's the work plan like? What's the schedule implications, the design schedule implications? And we're going to go to a highlighted project, a project that was recently completed in New York City, 1,000-foot tall, almost 3 million square foot building. Those of you who signed on, there's some handouts. I think I included a copy of one of the articles I wrote about this project called the Spiral. So you can read a little more in detail there. And so that's the highlighted project, and that's the example project. And again, we come back to workflow, details of workflow, more about benefits, schedule benefits, coordination benefits, innovation, innovative connections. How do we deal with it in the process? How do we deal with steel and concrete combined? Which this project that I'm talking about had that also. And then section 10 to 12, we're going to get into the QNEC add-on software that helps us all. This is about linking the fabrication modeling into the design modeling. In other words, moving the Revit into a fabricator's model. What's the benefit? I'll get specific later, but these are the benefits. Faster bid process. No need for the bidders, whoever's bidding on the steel, to prepare their own individual bidding models, which is always the case on every project that I've been involved with. You get the bidder, 5 bidders, whatever, submitting 5 bids, and they all have different tonnages, and they all have different piece counts, and the client turns to me as the engineer, what's wrong with your drawings? No one understands it. Uniformity of bids. Well, if everyone's working off of the same model, then there's no question on tonnage, there's no question on piece count, and there's very few questions in general, because we've given them a model that they understand and work with typically, which is a fabricator's model, not engineer's models. More accurate bids, uniform bids. Now we get into the schedule improvements. There's a shorter time frame, and I'll show it to you, a shorter time frame from fabricator selection to the start of fabrication. No need for the fabricator again to create their own model. Very few RFIs. If we're giving them a Tekla model of a, say, I'll let them use these words interchangeably, a fabricator's model or connected model or a Tekla model, they're all the same model. And mill orders are released sooner, much sooner. There's no delay due to shop drawing production, and you'll see why. Shop drawings are done way in advance. No delay due to delegated connection design. Conventional jobs, old-fashioned jobs, engineer walks away, job goes to the fabricator, they bring on their detailer, and the detailer's engineer, and then the questions and the extras start flowing. And it's all gets eliminated. If there's no delegated design, there's no delay in reviewing, call it the delegated engineer's calcs. So these are big deals. And one of the biggest benefits is while we're doing this, and this is directed to the architects in the room, the coordination process is greatly improved. And it's not just architecture and structure, it's architecture and MEP and structure. Okay, big picture, the old way. Everybody starts their work, I just called it analysis and design. Engineer of record makes framing decisions, not necessarily focused on connections. You may not be smart enough to focus on connections, but you're focusing on big picture, member sizing. Then you begin your 3D modeling. Like I said earlier, most of us use Revit. What did I just do? And then finally, it goes out to bid. Steel fabricator steps in, takes over the whole process, starts to submit shop drawings and calculate and RFIs. So what are we doing different here? Well, we're taking this third step and we're gonna start earlier. It's nothing more than that. Now, if you're starting it earlier, that there's no fabricator on board, well, someone's gotta start the connection design process. Someone's gotta start the modeling in the software that fabricators want to see, SDS2, Tekla, whatever. All of that starts to happen earlier. So I have a little schedule here, but let me go through the schedule and I'll tell you a first-hand experience on the big spiral job in New York. So all the red stuff is the conventional, schematic, DD, CD, you've seen this 100 times, moves into construction. With this process, we're starting something early. How early? That's a variable. What are we starting? The first thing we're doing, we're taking responsibility for connection engineering. And we have to start our calcs. The earlier we start, every job's different, we know that, bigger jobs, smaller jobs. The earlier we start, the sooner we get it out of the way. There's different steps in that process. First it's concepts, before you lead into final connection engineering. But it really should, doesn't have to, it should start early. Because if you're gonna do it already, you might as well try to gain the schedule improvements. Let's go to the next slide. After that, after you get your connection engineering moving forward, and of course I'll get to how we did the connection engineering, because we're just mainly with design engineers. Not every design engineer has the capability of doing connection engineering, so that introduces a whole separate question here. But after we get the initial let's call it grouping of connections and the connection concepts behind us, we could then start to input it into a Tekla SDS2 or whatever you want to call it. Let's just call it fabricator's model. Now, the projects that we work on are large projects. 1,000-foot tall buildings, could be shorter, could be taller, huge in area. So there's, obviously the entire project's not fabricated at once. It's broken down, sliced up into a number of areas. And so the next step is work, I call it the tiers. I mean, usually tiers are just 2 floors, but this is a different use of the terminology. The tier could be 10 floors. We took a 65-story building for all intents and purposes, broke it up into 10-story groupings, and the goal was, let's connect, have the connections in the fabricator's model for the full tier 1 before the fabricator is selected. So if you look at the schedule here, it says tier 1 connected, and there's a line that leads down to steel award. So when the steel award happened, we hand the fabricator tier 1 and the mill order. Now you can see what happens. What happens is simple. They do a quick process of generating the paper shop drawings, but the shop drawings are effectively all done. It's in the Tekla model. You just have to organize it. And they get the mill order in immediately, and depending who's supplying the steel, they can move into fabrication as fast as they get the steel. Because the shop drawings effectively are in the model. The model is done by the engineer of record. Connections are done by the engineer of record. There's a very quick, simple paper shop drawing process, because fabricators have to add lifting lugs and some other miscellaneous items that you don't find on the structural design documents, but that's usually temporary means and methods kind of stuff. And it's very quick, and we move into fabricating the first tier, what I'm calling the first tier. Now, from steel award to first steel start of erection on the job, obviously there's many issues that could complicate that. Foundations could be a 2-year process, right? But typically speaking, what I see, this can be a 5 to 6 month lag before you get the steel on site due to fabrication. Now these are big jobs, 30, 40,000 tons of steel. On a smaller job, it's proportionally smaller, but there still is the benefit. So this, in any case, it takes a minimum on the projects I'm talking about 5 months. And then the process flows, because you got past tier 1. While they are fabricating tier 1, we're already working on tier 2. And you're staying ahead of the game. Now, this is not the only way to move a project along. In this project, I'll just go back a bit. Here we go. We started the bidding at the end of design development. Now you say, oh, that's early. Bidding is not the contract. They're preparing a price, but you're not signing on the dotted line. So you could bid at the end of design development. When you sign on the dotted line, again in this example, we were at 50% CD. It's not bad, because in theory, let's hope everything works theoretically, but in theory, when you're at 50% CD, you should not be doing final design of your steel. Hopefully you're doing window and door schedules and things like that, and coordinating with MEP, but the design should be done for the most part. And the way we sliced it up, we had some loose ends at the upper half of the building, but there were allowances made in the bid for that, but the bottom, ready to go. The lower tiers. So in this early model, I'm saying we start the bid at end of DD, select the fabricator in the middle of CD. And that's what's shown here with these vertical lines. Steel bid, whenever, steel award, selection of the fabricator, that's at 50% CD. And that's, in this example, we had 5 months to first steel on the job. Now, I'll give you another example. Let's compare this process, same bidding date. So that's what you see here on the screen. Is my cursor showing up? No. Can you tell me if you see my cursor there? No? That's not good.
Most presenters have been using a laser pointer.
Oh. Maybe you could go out and get tech to bring the, oh, there it is. Let's try that. All right, sorry about that, I was pointing to the other one. So, in this scheme, I was saying, we bid at a point in time, it's on the other slide, at end of DD. There we go, end of DD, follow the line down, go to the next slide, please. And, am I blocking anyone? Sorry.
You're fine.
All right, I'll get sit down. So, the steel bid was then, we said there's a 5-month gap from steel award to first start of erection, typically 5 months. I call that the minimum. If it's a smaller job, it'll be 3 or 4 months. Now, take another scenario. We go down here. This is the second scenario. If we start the bid at the same time, whatever that date is, let's see what happens on the next page. Second scenario, conventional steel bid. Now, this is conventional, not meaning we're doing it the old-fashioned way. Old-fashioned way, we're not doing the connections, we're not doing the technical modeling, but we bid it at DD. Well, all of a sudden you got this extra step in here. You gotta make the calcs, you gotta do shop drawing production, you have to do mill orders, and connection calcs is a big deal, because I'm the one that always struggles with that. And this stuff adds 5 to 6 months to the process. So everything down the line gets delayed 5 to 6 months, in addition to what I said was the initial 5 to 6 months. So here we go, 5 and 5 is 10, or 5 and a half and 5 and a half is 11. That's the difference. Next slide. That's if you don't take on the responsibility of the connection work. Now, where are we here? And I'm saying, and this is, you could bid at the end of DD, you could bid at CD, bid whatever you guys want. I say you guys, whatever the client wants. But if you want to speed up the process, you take this out, connection calcs, shop drawings, and mill order, take it out. It's about half a year, and push it into the engineer of records responsibility. And push it out and start it early. If you just push it out and let the engineer of record do it, you're not gaining anything. So why do it? Well, I'll give you reasons why you should do it, but I lost my laser. Okay, does this work? Can I advance this slide?
I could do it for you.
Okay, there we go. So we're saying this is the culprit of all the extended length of time. Now let's go to the next slide. Now you understand the schedule, you understand what I'm driving for, to make the engineer of record responsible for connection engineering and the technical modeling. And it always irked me. We do all this nice engineering, and then give it to a fabricator who's super qualified to fabricate, and he hands it off to this engineering team. Years ago, the engineering team used to be in the fabricator's office. Now, they're sitting in India somewhere, or Eastern Europe, for South America. Most of the fabricators got rid of their engineers on staff, and things don't go well. And it kind of irks me. We do this sophisticated engineering, yet when it comes down to the nuts and bolts, someone else is doing it, and when we get the calcs, we're never happy with it. And now compare that, and I never worked in the automotive industry, but I get the impression the automotive industry, they have a 3D model of the car down to the nuts and bolts. And it's all engineered together, or the aerospace industry. And I don't know why we're so much less advanced than the other industries, but we're getting there. And I think this process will help us get there and control our destiny and get a better product. So, I was talking about a particular project in New York City. I don't know if any of you know the buildings that have gone up in New York, but this is called the Spiral. It's roughly 2.8 million square feet. It's a big building, 31,000 tons of steel without connections and more. 25,000 members, 50,000 connections. Obviously a big job. And nice job with all these terraces, complicated job. Let me show you a little more about it, and then I'll tell you how we dealt with this. So you remember I said we break it into tiers, 1, 2, 3, 4, 5 sections. The bottom tier was quite complicated. It's the biggest footprint. All these red zones are areas of mechanical floors, mechanical electrical equipment, and we have a lot of structure. We call it outriggers. Those of you who don't know, there's heavy truss work. The very complex areas of the building. But this building had a complexity that I have never seen in all the years I'm working. These spirals around, the spiraling terraces around the perimeter, like you saw back on this picture, resulted in, it is literally spiraling all around, and every time you pass those terraces, the building shrunk a little bit. So every floor was different, framing-wise. And usually people say, oh, I got a typical floor, 5 to 500. Right? We used to price back in the original, maybe some people do it that way, when we give a fee, we see how many different floor plans are there. Right? You still do that? It makes sense. I had a number. My old boss would say, how many floor plans? No, $10,000 a floor. Okay. Well, on this job, I had 65 floors and I have 65 plans. So it was messy. And that was because of the terraces. And if you look closely on this picture, the columns, and this had to do with the architecture and the terraces, the columns were never supposed to show through in the finished building. So it had to slope inboard and slope back outboard. It looked like somebody went there and pushed the column in, and they kept moving up the building. It really looked like it was a damaged building. But that's what made it complex, but that's what gave it its beauty. So I'm going to show you 5 floors quickly. I'd like you to focus on what I call the horizontal truss work. And depending upon where those terraces, here's the terrace, depending upon where those spiraling terraces are, that's where you have the sloping columns. Sloping columns create forces that want to push or pull on the building locally. And you can see these horizontal trusses just vary all over the place based upon where the terraces are, which resulted in every floor is different. Every floor different framing, etc. That just made my life complex. And of course, fabricator, increased cost, but it's a beautiful building. The other thing, and I'll just mention it now, the project was being constructed in the middle of COVID, and that was not expected. And the owner, Tishman Spire, very competent, experienced owner, agreed with Turner Construction. We're gonna have the engineer of record take responsibility for all the connections. Obviously, this wasn't the first job I've done that way. And we're gonna do the full technical modeling as shown through. And they said, great, you do it, guys. Because why? Well, what a coincidence. They signed up Pfizer to be the prime tenant. They were in a different place in Manhattan, a very old building, and they said they're gonna move to this beautiful building. The bad news is, they had liquidated damages if they don't turn over the building to them when they're ready to move in. And then COVID started, and the city shut down construction for months. And then they opened up construction, and all the laborers were getting sick. You'd work 3 days, and then the whole group got sick. And it was terrible. So to be blunt, what saved everyone's ass is with this process. Because by the time we got to that point in time, and by the way, I had the same problem. My people were not coming. They were the construction was proceeding in this slow motion, but all the engineers were already locked out in their office, working from home. There's a new way of working for us. What saved this project? We were well advanced in producing the Tekla model and the connection engineering. Although construction had just started, in construction in the field, we advanced it. It was removed, that whole heavy duty calculation review and shop drawing review was just taken away from the critical path. And the fabricator was down in Virginia, and they got this deal, and they were working through COVID. There was people on site who couldn't work. In any case, they met the move-in date, and there were no liquidated damages. And that's all bunch of coincidences that they selected this process, and the other coincidence was COVID, and all of this came together. So that's my little story. So why and how does this process help? So let's get into the nitty-gritty, more than just theory. So the job starts with a Revit model. When we get our Tekla team involved, we do an IFC export. By the way, this is the Revit model for just a simple component. And I'll get a little more specific momentarily. And then they do an IFC import, and then they make, your terminology, the unconnected model. It's a Tekla model, fabricator's model, no connections, but it's used for the mill order. And ultimately, you get the connections in, you get your nuts and bolts in, and this is the fabricator's model, the Tekla model. So you can see it looks kind of different, right? Now, a lot of things come to mind. And everything that I was talking about earlier, the coordination benefits, et cetera. When you see this during the design process, when the consultants see it, when the mechanical engineer sees, and I'll show you very specific details of the mechanical floors, and they're trying to route heavy piping, makes a world of a difference. So, the workflow, let's do a brief summary here. The Revit, I'm gonna, you know what they say when you do a presentation, never read what's on the screen, but I'm gonna read what's on the screen. Revit-based project would advance into the DD phase at least to 50% DD. Now, that's the first rule we violated here. We started at the beginning of DD with the process, but it's okay, as long as everyone is in sync. Everyone, the design team, and everyone's working together. You know what the schedule implications are. You know when you need your information. So, you got to advance your Revit work into the DD phase, preferably up to 50% DD, if not 100% DD. At this point, steel fabricator can start to generate Tekla unconnected models from the Revit model. And it uses the process I mentioned earlier. The IFC export from Revit would be created, imported into the steel detailing model. Again, I keep changing terminology. Imported members are then checked for connection sizing and location. Now, you'll all hate, the architects, you'll hate me for this, but the Revit model lies. The Tekla model doesn't. No Tekla modeler is going to put in anything in the Tekla model unless you know where it is. In Revit, we can lie. We'll just put it in based on the architectural background. Looks like it is, but you'll leave it undimensioned and then you'll fill it in later. But at least the steel is engineered right and you just, okay, you don't have the exact location. So when we turn it over to the Tekla modelers, the first thing we get back is, where's the steel? Can I believe the drawing, the Revit model? If it says it's 10 feet from wherever, can I believe it? And I say, no, you gotta have the dimension on the drawing. And there's no dimension on the drawing. So I won't get into that. The point is, when you hand it off to the Tekla modelers, you're gonna have to know where it is. The model has to close dimensionally, and you sort all that stuff out. And I can tell you again from firsthand experience, when we go through the old-fashioned process, we get lots of RFIs related to dimensions. So this takes that out of the picture. Connection modeling can begin after the Tekla modelers sort out the dimensions that are lacking. And then the constructability issues, and I'll show you on the next slide what I'm talking about. You have to sort out the RFIs that says, I can't build that. There's no room to stick your hand in and get the bolt, or it's a lot more than that. That's huge connections, you need room for it. It's bumping into the neighboring member. That's all sorted out. Now, those are big deals, because if two members can't come together, you have to change the working point. You change the working point, you change the forces on the member, you have to re-engineer the member. You don't want to do that in the middle of the shop drawing process. So it's logical to get those things thought through and do it in the design stages. And then the connection modeling can be completed, turned over to the fabricator. So this terminology that I'm confusing everyone with, the Revit model view, the framing will not be at 100% complete, changes are likely to occur. Member ends are set back graphically. I'll show you what that means in a minute. Early mill order model. We call it a point-to-point model. It's a Tekla model, or similar, SDS2, whatever. But it doesn't have connections. But it's only an early mill order model. What's an early mill order model? What's a late mill order model? Early mill order models reserve a spot in the mill, but they're not rolling. And today's day and age, that's the facts of life. You want heavy steel that they roll infrequently, you better reserve a spot. Of course, maybe even reserve a price, but that's not my business. That's the fabricator. So early mill order model without connections. The actual mill does not happen at the mill run, doesn't happen at that stage. Fabricator's model, the final model, to call that the connected model, it's got the connections in there, that's what they call the fabrication model, not fabricator, fabrication model. Completely connected, okay? So now that I confuse everyone more, let's move on. So, let's go backwards. This is the Revit model plan view. This is the Revit model 3D view. These setbacks of the members from the joint, I don't know, it's arbitrary.
No, you said it, but it's something.
It's all general.
Yeah, it's graphical.
It's graphical so things don't hit each other, right? Picture looks better. IFC import, same thing. You get what you garbage in, garbage out, right? Setback, IFC import's the same thing, just IFC input, little improvement on the graphics. Next page. Then you take the IFC import, extend the members to the working points to confuse the picture. So everything gets overlaid. I asked the question, why do you guys do this? I don't know, they do it. But they do it because you want the working point, you want to see exactly where the working points are. You want to see what hits. And when you look at this, and look at this picture on the bottom, well, this is the connected model. You start to get a picture, what's bumped, what's hitting what, how far back you have to set it to get the connections in. So you got to start with the worst case scenario and weed out all the conflicts, constructability issues, and I'll show it to you right here, for real occurrence. Here's the Revit model, here's the fabrication model. Now it's in 3D above and below the 2D. We had to move the working points to get it to be buildable. We had to go back and re-engineer the members because the connections could not all meet at the same point. I think I have a better view in the next shot. Here it is. This is a close-up. We had to move the working points. This happens all the time with complex structure. And my point is really quite simple. Do it during design. Don't do it during shop drawings. Because then, of course, you're delaying the fabricator. The fabricator's making a claim, a delay claim. The delegated engineer who works for the fabricator has to redo things. He's going to claim an extra. Just get it out of the way. So, schedule benefits. Now it becomes a bigger picture. Framing adjustments. Inaccuracies are refined at this stage. Not in the shop drawing phase. Connection design is based upon the actual member positioning, not anticipated location that is not buildable. And now the connection design and the review is removed from the shop drawing phase. It's pushed, it's early now. It's in the early stages of design. Constructability issues are addressed before it becomes a problem, before it delays the fabricator. And the process avoids RFIs. I mean, the cost to clients for RFIs is like, it's so many dollars a sheet of paper, right? And this is what this is the claim. I had to submit 100 RFIs versus I submitted no RFIs or 10 RFIs. And that's what I hear all the time. And then the owner turns to me, why are you doing such a bad job? So look at reality here. Here's your Revit model. Here's your early mill order model with all the steel overlapping at the joint. And here's the real finished fabricator's model. Now, if you're a mechanical engineer, and you know these heavy trusses are usually on mechanical floors, they're trying to route piping and whatever else they have coming and going. And they're working at best with the Revit model. And they're sticking things into the corners. And then the reality comes and they want to chop holes in all these gusset plates. Now wouldn't it be better if we do it right the first time? So that's what we're pushing for. And finally, I can say we're making headway. I just went through this on a new job, and we pushed for this early connected model process. And client, smart client, experienced client, but he wanted to save money. He said, why are you asking so much money for it? And I said, I'm not asking you for a penny. Either you pay us or pay the fabricator and their engineer. And I guarantee you, you'll pay them more than you pay us, because we don't charge by the weight of RFIs. We give a fixed fee and we live like it, we go. But, I've had jobs where they didn't believe me, and they said, let's start with this process. And then when they got to the selection process, they went to the fabricator and we said, okay, we had our engineer make this preliminary technical model, whatever you want to call it. But if you don't want it, tell us how much it'll cost for you to generate your own technical model and make your own shop drawings and not use our engineer's model. So I was happy he did that because my fee was $2.5 million and their price came in at $5 million. So I knew what to charge on the next one. So, and that's without the extras for the RFI. So here's a great picture. Now this project that I'm showing you was, the core was really a concrete core with lots of embedded steel. So things get even more complicated when you get into that area because you see all these studs welded on and it's a whole different ballgame here. It's really, I don't know how you can coordinate so many different things. How you can get the steel coordinated with the rebar unless you're doing an actual fabrication level. Gotta watch my time. Now, aside from the connections, there's the bigger picture view, right? The components, the trusses. I was just showing you connections. But now, and this is pretty simple, the coordination benefits by the bottom of the page. Bottom of the page follows the table of contents. The coordination benefits, this is obvious. Look at the picture on the left, look at the picture on the right. You're trying to coordinate with the design team. By the way, trying to coordinate with the architects on the perimeter of the building, because this was a truss on the skin with the curtain wall and the attachments. I mean, it's, and then constructability of how to make attachments for curtain wall. Curtain wall anchors, obviously, when you're next to gussets like this, it may very well be attached to some steel plate versus when you're far away, it's probably embedded in the slab. But this makes it so clear. And it helps the curtain wall bidders, it helps the erectors. It's a world of a difference. Now, even the simple stuff. So the simple stuff, this is what a Revit model looks like. Here's a fabricator's model. You got the moment connections, you got top. On this project, for whatever reason, they chose not to use sheet metal post stops. They used a plate. I guess it was a little long to get to the edge. So they have the plates on there. And then, obviously, if you have a curtain wall anchor over here with next to the moment connection plates, you have to rethink it. And this way, you have time to rethink it. And then what about the column splice? And what if it's a heavy column splice? And again, these highly architectural projects with big columns, every nut and bolt can get in the way. And they do. More trusses. And again, the complications of these jobs are many different aspects. The beams don't connect it. These braces, what you see here, are really temporary bracing systems. They're embedded in the concrete core, but that's neither here nor there. During erection, the filler beams are sitting on the steel. They're not connected into the body of the steel. Well, you know, when you show it on your design package on the Revit model, you're not showing connections. It's just floating in midair out here above the girder. Obviously, you're putting in vertical posts to get it down to the steel. It's a whole different ballgame. Column splices. Now, I showed you how these columns are sloping in and out of the building. Again, the same thing. When you start to show actual welds and stiffeners, it's very different than a very simple Revit model. And in reality, it's moves the design process along quicker and smoother. So let's take it a step further. Let's look at a photograph compared to our models. I love this picture. So this is one of those outrigger floors. Here's the model, and here's this. So, and there's all sorts of air handlers and lots of huge equipment on this floor. And I know, I get the calls, okay, I'm gonna run my pipe right in the corner over there, or right in the corner over there, and they say, look, tell me how much room you got there, and I tell them, no room. It's gonna gusset plate. Gets worse. This is my favorite picture. Those of you who know steel, you want to guess what that skinny little piece is? That's a 14 by 730. The raw steel member. So you can imagine how big this thing is. It was, I think it weighed like 2,000 pounds. And why wasn't this versus just weld the thing into a big node? Because the liquidated damages and you can't stay on job. And you can see, I mean, these plates are 5 inches thick. So this is and these trusses were at the, well, like I said, it was a complicated job. These trusses were at the 5th floor, holding up 60 floors on top of it. So that's the nature of the beast. Now, if you engineer the connections, you could coordinate with the rest of the design team. This is temporary steel, so I don't want to waste time on this. This is in the core, it all gets covered with concrete in the end. But you have to coordinate this temporary steel with the rebar that's coming after. So there's a lot of, these walls were 16 inches thick between elevator banks, and we had to put the temporary steel there in such a way that it did not interfere with the rebar. So, I mean, with models like we're talking about, you're able to coordinate. Some more of the trusses, right? You could tell where the X is, that was the core, and here's the outrigger. This is what the floor looked like. Oh, you can't see the floor here. This is what the floor looked like. There were 3 of these outrigger levels where most of the work on connection engineering was at those floors. And the interesting thing, if you look at our engineering drawing, this is what we issued. Telling you had to go to a table to get the member size, you had the forces here. What does this picture tell you? Nothing. If you're a fabricator, you could then work with this picture and build this model. It tells you your tonnage, but it doesn't help anyone in the design process, trying to coordinate architecture and structure and MEP. And this, we had hundreds of these drawings. And the force is noted over here. So, I mean, the force doesn't tell you the size of the gusset plate, it tells the engineer the size of the gusset plate. Here's a better picture. I wrote this picture years ago, you didn't have it. Isn't it interesting? And then finally, innovative connections. And this, we learned a lot, the engineers, myself, and my team. There's one of the floors, and it happens quite a few times. Let's go back. You see the concrete core, right? You see complex connection here with build detail, right? Throughout the models, these corners here. Happens a few times as you go up the building. Now, those of you in the business, I'm sure you can tell me right away how you're going to make that connection. And the forces coming in here are huge. Go ahead, Here's reality. So, first thing I learned is a thing called, such a thing as a forging. Used to be castings. Now it's a forging. This is solid steel in red. So you don't have to infill a member with stiffeners and doublers and try to weld this to everything together and then find out, by the way, those of you who are not in the business, usually a surprise when they say steel cracks. Steel cracks. If you don't do the welding details correctly, they crack. The heavier the steel, they crack. Every heavy job I have cracked steel. You know, we sorted out in the end, but with a forging, solid steel is not cracked. So, And that, now I see, on many of the heavy-duty projects in the city, you get to, in New York City, where you get to these complex joints, every engineer's using forgings now. They're good quality, they're high strength, and you could deal with, and it is an old trick of the trade. It's obvious to those of us who are in the business. When this member could be very heavy, 14 members. Most of the force comes through the flanges. The flange can't reach the column in the corner because of the congestion. So there's a transition. This plate is 6 inches thick, and you transition and tapers back. So it's just a vertical weld to the forging. That's a shop weld, and then the field weld's out here, and if it's not a field weld, it will be bolted, but there's a temporary bolted connection here. But this is a field weld, but this let's call it gusset, converts the flange forces into web forces. Okay. Oh, another favorite. So the concrete. Now you gotta put the concrete on. How's all this gonna fit in between this rebar? Look at that. So once you have all this in the model, and this is one of the reasons why you don't bring the flanges in, even if you can connect it. I mean, if you want to connect the flanges, you can. You move and shift your working points, and then have the flange coming in. You won't have any continuity with any vertical rebar. So that's the other benefit of doing all of this during design, engineer of record, working with your concrete designers, get it all coordinated. Oh wow, can't believe I used up the whole hour. Automated connection design, I'm gonna turn it over to you. QNEC automates 80% of the framing. And we used it, because 80%, maybe 90%, is simple framing. With this job, probably closer to the 80%. The design team, how did we pull this off? Well, we were the engineer of record. We had our fabrication modeling team. They don't sit in the same office as us, but they've been in business for a long time. They know what they're doing. And they had a sub-consultant and other external WSP modeling teams, because we're a big company and you got to call in the resources that you need. When it comes to connection engineering, we have connection engineers, but we didn't have enough. We had to have a sub-consultant working for us. So anything goes wrong, there's no one to blame but ourselves. Full responsibility. Leah, I'm going to close with this, and I'll give you a whole 5 minutes. But they're practical and legal issues, and I'll just go to the first item. TECLA must match the contract documents. And the question is, and they always ask me, what is the contract document? Is it TECLA model? Is it the Revit model? Is it back to the TECLA fully connected model? I never have the answer, but they seem to work it out. It's changed over the years, but every job's the same. What's the contract documents? This client was very smart. At the very end, he said, okay, anything you issue, I expect 2 issuances at the same time. Contract document, which is the Revit model updated, TECLA model updated. They always have to be both issued at the same time, so no one can say, I found it on the TECLA model, I didn't find it on the Revit model, or vice versa. There's a whole bunch of other things here, but we could talk about it after. But there's a lot of questions, legal questions and practical questions. One more point, you only model what's shown in the Revit model. That's why we hand our model to the fabricator. If he wants to add on lifting lugs, etc., their responsibility. Then model comes back to us, it's a shared model. We have to check they didn't make other changes, which sometimes they do. It's just out of accident because they wanted to change something. So, you gotta be careful. And then the whole QA/QC process is a critical process here. Go ahead. Let me introduce Mike, if I talk too much. But
You can hear me here with the mic. So
really exciting to see this presentation. My background too, being in the industry for many years, seeing engineering firms like WSP drive this process forward is really interesting. But how many in the audience here are outside of the US, like Europe, companies? Yeah, I mean, like other parts of the world, engineers do the connection engineering and detailing, right? So I think in the US, where this is really what we're talking about here today is really an opportunity for the industry to improve. And we see this process of really connected models as really reducing risk for the UR. You might think of this as like a column interaction diagram, you know, your external forces going vertical and your capacity going to the right. But think of these processes of delegated connection design, mandated connection design, which is West Coast, to this early connected model. We think this is actually less risk, and the resiliency, that capacity for your company to manage this risk is actually greater. But here today, you know, we're kind of in the automation business to kind of automate a lot of the repetitive tasks that frees up the time for companies like, and Jeff's team to really focus on the complex, right? And you heard about all those, the great insights and knowledge they have around constructability and to really leverage this process. But what we're looking at is how can we take some of the expert systems of, you know, automating tasks such as like QA/QC of models and looking at the Revit model as a bridge and a step before this early connected model to really identify constructability issues. A lot of these things that build into, you know, the unconnected model handover. And so what we're doing at Connect is actually releasing a beta here, really announcing here at AU of a QA/QC review within Revit. And this is an ability for engineers to basically detect issues in their steel framing that identifies potential constructability issues in the Revit model. And when I say constructability issues, I'm talking about things such as you know, limit state checks that don't meet certain checks of the AISC code for like members. So in other words, if you have net section rupture checks on your bracing or on your shear connections. Also looking at erectability issues. Where's the column splice location? Did you model it in Revit at top of steel, or is it at 4'6" top of steel, which is where it needs to be from a fabrication erection position? So we have nearly 200 of these checks that will basically audit the Revit model for the engineer to identify these constructability issues. And so we're excited to, you know, work with WSP and as kind of our first driver of this workflow. And I see this in the future. This is really important because as companies are exploring these tools to connect, you know, Revit and Tekla together. I think there were some presentations yesterday from Goldbeck talking about, you know, leveraging the new granular data interoperability that Autodesk is doing. There's a lot more demand for this sharing of data between platforms, right? So this is all going in that direction of how do we make, you know, Revit delivering more constructible models and also be able to interoperate downstream with technologies that are delivering connected models. So just to kind of close this out, we're, you know, excited to hear about WSP's, you know, implementation of the early connected models. This is really a proven process in the industry. Other structural engineering firms are wanting to get on board. There's expertise you need to do this, but there's partners out in the industry to help you achieve that. And we think some of these technologies, what we're talking about with, you know, constructability review in Revit is like a stepping stone for engineers to really take that step closer to delivering more constructible models. So with that, I think we're right at one time.
So one of the instructions we were given is we're supposed to educate, we're not supposed to make a sales pitch. Right? So hopefully we met that goal. But it's an important point. You may be wondering, well, my engineers don't work with Tekla. Most engineers don't know, they don't have a Tekla modeling team. So how do you implement this process? And the process could be, I have this thing. How do you implement this process? So, and we're now here's the sales pitch. We're selling our expertise at Tekla to the industry. So if you're an engineer of record, working with architects, and you wanna get an early Tekla model, we've done this. Our competitor came to us and, well, we don't do Tekla, can you do it? And at the same time do connection engineering, and we'll work together, and you'll take out design documents, and there's no still fabricator on board yet. So we started, we learned a few things or two, and we now offer the service with QNEC involved. So anyone can do it now, even if you don't have the in-house capability. Go ahead.
Yeah, and I think that over the years has been a challenge of, engineers are already forced to have a lot of expert knowledge in a lot of different areas of structural systems and materials, and now sustainability and embodied carbon. So, but relying on think of yourselves as we're like master builder teams of the future, right? The master builder itself doesn't really exist in this world, but the master builder team does. So think of the industry as a whole. How do we team up to become like the master builder concept, which is really what this is, by using a team of experts to deliver that to the industry.